Hello students. Let's continue setting up the new character. Let's recall where we left off. The first issue that catches the eye is the rotation angle of all the skeletons. They are all facing in the same direction. And this direction does not depend on the direction of movement. I want each skeleton to look in the direction it is moving at the moment. So today, we'll work on correcting the movement mechanics. The movement of the first enemy suits me completely, so we'll leave the enemy move branch as it is. And for the skeleton, let's create a new one. Let's call it skeleton move. Let's attach it immediately to the skeleton base. That is, to the cube named enemy 2. Select the cube. Go to the object's properties. Delete the enemy move branch and instead connect the new one with the name skeleton move. We won't write the code from scratch. We have almost everything we need. Let's copy the contents of the enemy move branch here. Open the enemy move branch. Select all, copy to the clipboard by pressing Ctrl C. Go back to the skeleton move branch and press Ctrl V. If everything worked out, then let's go back to the enemy move branch and delete this group of nodes that trigger the animation. These blocks are not needed for the cubes. Let's return to the skeleton move branch. Let's outline the plan of action. Here's what we have now. The enemy moves across the screen in 4 directions. It calculates the direction and moves in the right direction using global axis. The enemy does not use rotation. I suggest redesigning the scheme as follows. Instead of calculating the direction for movement, we will calculate the angle for rotation. And the enemy will always move in one direction, along the local y-axis. In other words, always forward. But this time we will have to choose not from 4 directions, but from 8. Let's take a brief detour. And I'll tell you about orientation. Not about my orientation, but about orientation in space. Specifically for this, let's switch to a separate scene. You don't have to repeat after me, just watch. So, we have a character. And we need to understand how to measure, fix, or change the angle of rotation. We are now going to talk about the global coordinate system. And we will talk about it with respect to the z-axis. Because when rotating the character, we will only use this axis. The others do not interest us. On the screen, we can see the absolute angle of rotation. And right now it is 0. So, if the character is facing north, or in the positive direction of the global y-axis, that way, it means he is facing in the direction of 0 degrees. The global 0 on the z-axis is always there. Now let's see what happens if we rotate the character. Each key press adds 5 degrees to the current angle. And after a couple of presses, it becomes clear that the counterclockwise direction is positive. The values are increasing. They are recognizable. The character is looking strictly to the left, and this direction corresponds to an angle of 90 degrees. We continue to rotate until we reach the southern direction. It corresponds to a value of 180 degrees. What do you think the next value will be? No, you didn't guess. Next will be the negative half of the circle. And all values will mirror the left half, with the opposite sign. The eastern direction will correspond to an angle of minus 90 degrees. We've covered the basics. Now let's organize the rotation towards the sphere. We will rotate the character using the set object rotation block. And to calculate the desired direction, we will use the look at block. Connected to Get Object Location blocks. We will calculate the angle between the branch owner and the target, so we leave the first block empty and specify the sphere in the second one. Choose the y-axis. This is the front part of the character. This axis will be facing forward. Now we convert the obtained data into a rotation angle along the global axis. We take out the separate rotation block. Convert it to degrees. And since we are only interested in the rotation angle about the z-axis, we will need the separate block. That's it. From the z-axis channel, we can calculate the rotation angle towards the sphere at any time. We cannot connect it directly to the set rotation block. We need a rotation block. We switch it to the angle axis mode and degree measure. Set 1 in the z-axis. And connect the obtained angle to the angle input. We will rotate the object in real time, so we power this chain from the onUpdate block. Let's run around the sphere and see the result. The character always faces the sphere, and we can see the current rotation angle. In our game, enemies will not have the ability to rotate at any angle. We must limit them to 8 directions. Mathematics will help us as always. Let's divide the calculated rotation angle by 45. Round the result to the nearest whole number. And then multiply by 45. Now the character can only rotate at angles divisible by 45. I hope the theory is clear. Let's move on to practice. We have the skeleton move branch open, and we are mercilessly redesigning it. This section is responsible for the enemy's entry onto the field. We get the coordinates and decide which direction to move. Delete all movement blocks. And instead, connect rotation blocks. Set object rotation. We switch them to angle axis mode and degrees. Put one into the z-axis. Now let's input the necessary rotation angles depending on the direction. Label frames will greatly facilitate this task. For moving left, we need a 90-degree angle. For moving right, we specify -90. For moving down, we input 180. And for moving up, we leave it as 0. Let's check what we've got. The enemies spawn with the correct rotation. They all face the scene direction. Excellent. Now let's make them move in this direction. At the merge block, create 4 slots and connect all 4 chains. To take a step forward after turning in the right direction, connect the translate object block. Now we will move exclusively along the local y-axis, so check the local axis box. Put 0.01 into the y-axis. Now let's highlight this piece of code and delete it. It is responsible for selecting the direction using the old technology and is no longer needed here. Also, you can delete 2 variables that were used to calculate the distance to the player. Don't confuse the objects. Remove the variables only from the new cube named enemy2. Now the skeletons stop immediately after entering the field. Now they don't know what to do next. Let's explain to them what's what. Take out to get object location blocks. Leave the first one empty and specify the player in the second one. Connect them to the look-at block. Choose the y-axis. Convert the calculations to Euler degrees. Separate the z-axis. Divide it by 45. Round the result to the nearest integer. And multiply the rounding result by 45. Connect all of this to the rotation block. This time, set the mode to angle axis in degrees. Don't forget to put a unit into the z-axis. The last block related to rotation, set object rotation. Power this chain from the false channel, from the starting group. Right after the rotation, we need a forward movement block. You can copy it from the starting chain. The settings remain the same. Local y-axis and speed 0.01. Now, when the skeletons crawl onto the scene, the signal will reach this chain, and the enemies will hunt the player. There is one little problem left to fix. Skeletons moving in the 180-degree direction behave inadequately when changing direction. This is because currently, we are trying to calculate the rotation angle for the z-axis, but we have tilted this z-axis sideways. Because of this, we get such jerks. The direction vector to the object should be parallel to the ground. Or in other words, the z-axis, the direction vector, should be strictly perpendicular to the ground surface. In the test scene, this problem did not occur because the objects were of the same size and their centers were at the same height. Here we have a different situation. The player's center is at a height of 0.5, while the enemy's center is at a height of 0.4. Therefore, our angle calculation scheme will always have an incline. This tilt will depend on the distance between the objects. No perfectionist can accept and reconcile with such a setup. Let's fix this problem. We'll simply divide the obtained coordinates from the enemy into separate axes and change the value along the z-axis to 0.5. Then the angle will be measured from the same position but from a different height. This height will now match the player's height, and the problem will disappear.
Perfect.
Now, it's break time. Don't get bored. Bye-bye.